So, for the Wiener filter, now what we do that we have the constituent, the terms. So, with the help of that we can actually write this the mean square error J W in a more compact way. The first term is the variance of the desired signal. The second and the third term, they are nothing but the cross of that weight and the vector theta. Theta is the cross correlation vector between the observed signal and the desired signal. Okay. And at the end we get that the term involving the phi, which is the autocorrelation matrix of that observed signal x n. So, what we get here, that we get a expression which is quadratic function of W, that W are the tap weights here, and what is the specific actually the quality of that quadratic function, that it gives us a global minima. So, to understand that, let us take just a simple case that where the dimension is 1. So, if I take a function in dimension, the tap weight dimension is 1, that means it involves with only say W square, and W also could be there. So, it is a function of the form A W plus say B W square. Okay. So, it would be a parabolic function, okay, a parabola and a straight line, a combination of that. Now, being a parabola, it has a minima here, okay, and this global minima that we can reach there by actually taking the derivative, or to be more specific, in this case we need to take the partial derivative for each of this weight when W is having actually the multidimensional one. Okay. So, what we get actually that J W, it is a surface, it is a, or we can tell it is a hyperplane, and this function has a global minima of it, and at that minima the gradient at this point would be 0 at this point. Okay. So, we exploit that situation. So, we want to find out the value of the weight where the gradient would be 0, and thereby we would like to find out that the point where that value is minima. Okay. So, we are using that fact. So, we have to take actually the derivative of that objective function J W. So, let us now proceed with that, and let us see that if we take that derivative, what are the terms we get here. Okay. So, we get first that if we take the derivative of that the term involving the theta transposed and the weight, that for each of these component, say W 0, W 1 and all, that taking the derivative with respect to the vector means that we are taking actually the derivative with respect to each of these terms and then putting it back in the vector form. Okay. So, if we do it manually, we can easily check that for each of them that we get the corresponding value of the theta. That means, say if I look at this term, it would look like that, say with say W 0 into say theta 0. Okay. And if we take derivative of that with respect to W 0, so we would get theta 0. Okay. So, if we perform it in this way, or let us take it in a more general way. If we take it that with respect to say for each of these term, say we have theta I here. So, here it would be minus I. Okay. So, we get the terms like this, okay, each of these terms. So, at the end if we combine each one of them, then we get the vector theta after taking the derivative. Okay. And because that this thing is a scalar, actually this the product is the scalar quantity, that w t theta and theta t w both gives the same result. So, here also we get after the derivative the vector theta. Okay. And for that term, that the last term, that involving the autocorrelation matrix, we get it to that phi w. Okay. And here we have actually omitted one part, that is what happens if we take the derivative of this one. Actually we have not mentioned about it, because see this one is what? It is the standard deviation of the desired signal. Now, it is already given, and whatever may be the tap weight, it will not change. So, if we take the derivative would be 0, okay? Or in other words, there would not be any change in the variance of the desired signal, even if we change the tap weights. Okay? So, this way we get actually the derivative of all the 4 terms involved in J w. Okay. So, now let us then proceed and see that what we get out of it. We substitute those values, that by substituting those values of that derivative of those 4 terms, we get for the Wiener filter that we get the first term, that derivative of the standard deviation of the desired signal contribute to 0, and for the second and third term, that is contributing minus 2 theta, and the fourth term is contributing this part, that 2 phi w. Okay. Now, by scaling it and changing the side, that means taking this theta in the right hand side, we can write it in this form, that phi w 0 equal to that the vector theta. So, this actually equation, this equation is known as that Wiener-Hoff equation. Okay. And here one good part actually what we get out of this exercise, that the weights what we told, the weights we are able to get in terms of a set of linear equations. Okay. And if we check the dimensionality, what we have, phi is the having dimension m by n, okay, and this w 0 having m by 1, and theta also is having dimension m by 1. So, for that m weights, we have actually a set of m equations. So, by solving simply these equations, set of m equations, we are able to get that the value of the w 0 or optimal value of the weight. Now, here we added this suffix here, that 0, just to indicate that this is the optimal weight, okay, or the tap weight which gives the minimum for the error function, that this J W. Okay. And here is another name for this, this is called also the normal equation. Okay. Hope you recall that with the tap weight what we are trying to do, we are actually getting something called d tilde n, okay, that is the desired value which should be as close as possible to d n. Okay. Thereby we are minimizing the noise. Now, let us take that d n is a vector, say if the d n, this is the d n, that is a vector, okay, and say d tilde n is going in this direction. Now, the error would be minimum when actually this is the error, okay, that if this is d tilde n, then this one would be the error. The error would be minimum when actually this vector is perpendicular. Okay. So, that's why that we call this equation as normal equation. That means the prediction what is happening and the error, these two would be normal at this condition, and that is how the name came as normal equation. Okay. So, this is how we get this Wienerhoff equation or the normal equations, and by solving them these equations, set of equations, we get the optimal weight vector W 0 equal to phi inverse theta. Okay. So, at the end of this exercise we get the value theta. Now, let us try to address that how actually we can have some d and for the set of actually solving this equation or to calculate the tap weight. Okay. Let us go back to our the old example of ECG signal. I hope we recall that the ECG signal is having that P, Q, R, S and T waves. This is P, Q, R, S, T, and because of different kind of noises, say high frequency noise, then we have that power hum, actually lot of noises are added with it and it got smeared in this way. Okay. We can say again for the next wave the P is coming, it got smeared, this is the signal. So, in this case we are unable to figure out that the desired signal. If we could get that, then we do not need to do all such job of optimal filtering. But what we can do, we can actually easily get some estimate of the desired signal from this corrupted signal by some approximation. For example, that from 1 t to the P wave of the next bit, in between this part is actually isoelectric line, there is no activity is there. So, if we want to take that characteristics of the noise, we can just observe this part, we can take it out as a sample of the noise block where no signal is there. Okay. Now, if we want to get the desired signal, that is the ECG signal in this case, then how we can approximate? We can put it with a straight line, and then to actually eliminate the effect of actually noise, or to reduce the effect of noise, we can have straight line approximations that will, by few line segments, we can approximate each of these . So, we can get an approximate value of the ECG signal, which may not be very accurate, but close enough to serve as a that the desired signal d n. Okay. So, in practice we can actually get some desired signal out of the corrupted signal, but such kind of approximation is not natural. So, they cannot serve as actually for the real processing. With the help of that what we would like to do, we would like to calculate actually that d tilde, we would like to calculate d tilde n, and that one would be smooth, and after the optimal filtering we can actually make use of that, and that we can proceed with that for further processing. So, let us now move forward. We see that after this part, that what we have to do. The first thing we are interested in, that what is the minimum value of the error. We wanted to minimize that J w, and we found that tap weight where the error will be minimum. So, first thing we would like to know that what is this minimum error. Okay. So, this minimum error we have taken here, that J mean, and for that we are simply replacing the tap weight with the optimal value of the tap weight, and that is W 0, we know that is equal to phi inverse then theta. Okay. So, we need to use that proper notation for that, and as we take it, that for this first we replace actually W with W 0. So, it has, we know, with 4 terms. The first term is that variance of the desired signal, and then we have the 2 cross terms, that between the theta and that W 0, and theta is the cross correlation between that observed signal and the desired signal, and then we have the autocorrelation matrix, this 4th term using the autocorrelation matrix. Okay. So, with that as we replace it, the W 0 in the 3rd actually line, that here we actually replace W 0 with this value, and then we make use of the fact that if we have 2 matrices A and B transposed, the result would be B transposed A transposed. Okay. So, we make use of that. So, that way that we keep it here. Out of that, there is no change in actually that phi or phi inverse, because phi is a actually symmetric kind of matrix. So, here the transpose does not make any difference. Okay. And we rewrite that using this equation, and what we get, that these 2 terms, the second and the third terms, they are equal, and after simplification of the 4th term, we get that in magnitude the fourth term is also same as these two terms, only thing the sign is different. So, two of them they cancel with each other and we are left with this quantity. Okay. So, this is the minimum error we get. Okay. So, this is the interesting thing that we have to look at, and then we proceed and we see that the Wiener filter, for that the Wiener-Hopf equation, it can be written in different ways. That one of the most popular way is that in terms of matrix and in terms of vectors, that is what we have given, that we have actually given the autocorrelation matrix multiplied by the tap weights, and in the right hand side we are getting that cross correlation vector. Okay. And here for the simplicity sake you can actually write it in terms of the terms that m minus 1 and 1 minus m, they are that these two terms they are the same. So, we can replace it in that way also. Okay. So, then we can appreciate that it is actually that if we take transposed, that it will not do any change. Okay. And the same thing can be written as a set of linear equations. So, both are having the same amount of information, and this is the way we can actually express that Wiener filter or the optimal filter. Okay. Thank you.